So, good afternoon and welcome to this session of, say, digital electronics, in which we are going to study some of the circuits of sequential circuits, right? Sequential circuits. Now, where we require the circuits to work according to the feedback given to it, right? So, these circuits are basically called as flip-flops. Flip-flops, right? We will be studying from the basics of it, and we will be using the gates to employ, say, gates to implement those flip-flops, right? So we'll be starting with that. Let me ask, am I audible loud and clear so that we can start with this? So, yeah, am I audible? Anybody can reply?
Yes, sir.
Thank you. So we know what is a NOR gate, right? So we'll be using this gate to implement this flip-flops, and I will tell you why these circuits are called as flip-flops. So you will be using this. So you know what is a NOR gate and what is a NAND gate. So we will be using those gates. So let us start with that. Now, a NOR gate, something is looks like this. So we are having a NOR gate like this, two inputs and one output. So in a NOR gate, we can make this circuit in the mode of, say, we call it as a disable mode, right? So disable state. So we can convert this circuit, this gate, to a disable state. Now, how we are going to do that? Let me tell you. So if you put one of the terminal of NOR gate to high. So I will keep this one terminal to high. Then what happens? It is to a don't care condition, whether it is 0 or 1, the output of this NOR gate is going to be 0. And that is why we call this as the disable condition, right? What we have done, we have kept one of the terminal of a NOR gate to high, or say 1, or we have connected to, say, plus VCC in that case, to understand. So if you connect one of the input to an of a NOR gate to plus VCC, and the second input is don't care, means whether it is 0 or 1, it doesn't make a difference. If it is 0 or 1, if it doesn't make a difference, but the output will remain to 0. Since the output remains to 0, that is why we call this situation of a gate as the disable condition, right? So we call this as a disable state, right? So we call this state as a disable state, and this is for, say, NOR gate. So as far as NAND gate is concerned, if you want to use the same NAND gate, somebody is joining over here. Yeah. So if we need to use a NAND gate for this circuit, so we can use this NAND gate in a different condition, and that we are going to call it as the enable state, right? So for a NAND gate, we know this type of a symbol of a NAND gate. So we are having a NAND gate like this. I guess it is visible. So we are having two inputs like this and a one output, right? So to make this NAND gate to enable state, what we need to do is we just expect to give one of the input to connect to ground, or say 0. So if you connect one of the input of a NAND gate to 0 or ground, then whether this another input is 1 or 0, it doesn't make a difference. The output of this NAND gate will be high, will remain high as it is, and therefore it is called as the enable condition, right? So enable state, or say enable state, or enable condition, right? So this is how we can use these two gates in different mode. So for NOR gate, we can use this NOR gate in a disable state, right? And similarly, for a NAND gate, we can use this as for the enable gate. And the condition is one of the input of a NOR gate is kept to high, then we don't have to care about the another input, whether it is 0 or 1, the output of that NOR gate will remain 0, and therefore it will remain low, and therefore it is called as the disable state. Similarly, for a NAND gate, whenever one of the input is kept to ground, or if it is kept to low or zero or given zero, then without caring for the another input, whether it is one or zero, the output will remain at high or one, right? And therefore, if the output remains high, then that condition is called as the enable state. And the condition for the NOR gate is called as the disable state, or say the disable condition. Right? Why we are talking in this form? Because we need to use this NAND and NOR gate for designing or for the implementation of RS flip flop. So I'm going to tell you the circuit for that. So I guess you have understood that how we can use this NOR gate in disable state and this NAND gate for an enable state. These are the two conditions where we are employing these NOR and NAND gates to design or to implement the flip flops. And I'm going to tell you why those circuits are called as the flip flops, right? So just hold for a second. Yeah. Yeah. So we are not now going to use this NOR gate to design the flip flops, and we call them as RS flip flop or SR flip flop, right? So let us try for that. So RS flip flop, and we'll study why I have taught you this condition and why these are called as, say, flip flops, right? So this is flip flop. RS flip flop. Now, to design this circuit, what we are going to use is we are going to use two NOR gates, right? So NOR gates, and just drawing the symbols of NOR gates over here. So this is one NOR gate having two inputs. Similarly, I will be using another NOR gate, and accordingly, like, yeah, so it is having another output. These are two inputs of this two NOR gates. So I'm having two NOR gates like this, okay, and uh, two outputs of them. Now what I will do is I will feed back the output of the NOR gate back to the input like this. So just look at this, how I'm doing this. So I need to feed back the output of the second NOR gate, like, to the first. Yeah, so for second output of the second NOR gate, I am feeding it back to the first input of the first, and the output of the first NOR gate, like this, I am feeding it back to the second gate, like this. So I've just tried to short this. The output of the first NOR gate is being feed back to the input of the second NOR gate, whereas the output of the second NOR gate, as you are able to see, I'm feeding it back to the input of the first gate, right? So this is what we call them. So I will name this. I'm taking this as R. I'm putting here the name as R, and I'm putting here as S. Why I'm putting R and S, I will also going to tell you. So R means reset and S means set, right? And the output of the first NOR gate, I am taking it as Q, whereas the output of the second NOR gate, I am putting as Q complement. So we are having two outputs and two inputs, right? So we are calling it R, S, Q, and Q bar. When I need to make the truth table of it, what I come to know is I will be having two inputs like this, and say the two outputs. So R, S, and two outputs where Q and Q bar can be taken as. So this is R, this is S, this is the Q output over there, and this is the Q bar. So we expect that Q and Q bar should be opposite to each other, right? So this is how we are going to design. Now let us start with this. If I want the inputs to be given. So the probabilities to the of giving the input to this circuit will be, four times as we have given earlier. So it might be 00, 01, 10, and 11. So these are the four probabilities in which we are expecting to give the inputs to the circuit, right? So I am giving this inputs and we'll check what happens to that, right? So if I give R and S equal to 0, 0. So R and S means R is equal to 0 and S is equal to 0. Now, just for consideration, because these are called as sequential circuits, means which depends on the feedback, which depends on the output of the circuit, and that output is being feedback to the circuit, right? So one of the output will imagine that it is one. So if it is one, say this the output of q is 1. So if it is supposed to be 1, which implies that the input to the second of the NOR gate is equal to say is equal to high, right? So if this is high, which means that this has gone to a disabled state, and this will give you equal to 0, right? So I've just imagined one of the output of say the circuit, that is NOR gate, that is equal to that is we call it as a Q, is high right now. So if it is high, then the input to this one input to the second NOR gate will be high. So if one of the input is high as per this condition, if one of the input is high, then this NOR gate is going to land in a disable condition, right? And if it is in disable condition, the output of that is supposed to be 0. Similarly, this 0 is in feedback to this circuit, to this NOR gate, so it will become 0. And if it is 0, so 0 and 0 will give you high, which implies that there is no change. So even if you change, so whenever we apply input 0, 0 to this gate, the output remains constant. Now let us alter this. If I say that this is equal to 0, this is equal to 1, and this is equal to 0. Now what happens? Again we are applying 0, 0 over here. So depending on the condition of the output, right? So this is 1. So if this output is 1, then the 1 will be given to here. Now the first NOR gate will go in the disable condition, implies that this Q will become 0, and if it is 0, the input to the another gate, this will become 0, and if both are 0, then the output will remain 1, right? So it shows that whenever we apply this first condition to put R and S both equal to 0, the output is no change, no change. So we call it as no change, no, no. I guess it is not visible, and I will just write NC. NC means no change, right? So if Q is there, then it is also no change, and Q bar is also no change, right? So both will remain opposite. And as you are able to see, when Q equal to 0, Q bar equal to 1, and when Q bar equal to 0, it becomes 1. So they are opposite to each other, and therefore they are being named as Q and Q bar. Now just imagine what happens if you go on changing and give the second say second condition, that is 0 and 1. So we need to know what is the initial condition of the output, and then only we can say that the output is going to change. So let us assume for the second condition, that is when R equal to 0 and S equal to 1. So now I am putting R equal to 0 and S equal to 1, right? So as soon as I put S equal to 1, right, and R equal to 0. So if S equal to 1 means one of the input of this second NOR gate is going to be high. And if it is high, then without caring for the second input, this gate is going to land in this disabled state. Now, if it is disabled state, then this Q bar is going to be 0. And if this is 0, so 0 is our input to the first NOR gate. So both will become 0, and the output of Q will change to 1. Now, this condition of changing the output from 0 to 1 is called as set, right? So I will write here, if when we apply R and S, R equal to 0 and S equal to 1, then the flip-flop set. So I will writing over here set, SET, set. So the flip-flop sets, it becomes high, right? So this is the second condition when we are applying R equal to 0 and S equal to 1. The output, so we are expecting to check only this output. So that is why we call this as the output sets, right? And therefore the name is over here is S, right? So this is S. Now coming to the third condition in which we are expecting to apply that R equal to 1 and S equal to 0. Again, the initial condition of the output should be taken into consideration, and here we are going to take Q equal to 1 and Q bar equal to 0, because then only we will be able to visualize whether the output is going to change or not, right? So let us start with that. So we are applying, initially we are applying R equal to 1 and S equal to 0. So R equal to 1 and S equal to 0. As I told you, one of the input of a NOR gate, if it is kept at high position, then this gate becomes disabled and the output switches to 0 without caring for the other input. So if one of the inputs is are high, one of the inputs to a NOR gate is high at a time, so that particular NOR gate, according to this condition, will land in disable condition. The output switches to 0. When we apply this 0 over here, both the inputs to this gate is 0 and the Q bar changes to 1. Now, as you are able to see, the output of this NOR gate is now reset, right? If it is 0, then we call it as reset. So the output of Q, since we are going to change or check only the Q terminal, so we call it as reset, right? So this is the third situation. So when R equal to 1 and S equal to 0, the flip-flop resets, and therefore the name is there, that is R. So we are having this terminal as reset terminal, this terminal as set terminal. This is actually the output which we are expecting to check, and this is the complement of that output, right? So these are the three conditions which we applied. We have seen when we put R equal to 0 and S equal to 0, we have no change, means whatever the output was there earlier remains same, and therefore we call it as there is no change in the output, right? So there is no change in the output, and I have written over here NC, right? So when we apply R equal to 0 and S equal to 0, the output remains same, and we call it as the no change situation. Second situation in which we are applying R equal to 0 and S equal to 1, which means that the set terminal is kept at high or 1. So when I put this S equal to 1, this gate is going to be disabled. The output of it is going to 0. And if we apply 0, 0 on both the sides, we'll have 1, which says that the flip-flop sets, right? So I put here when R equal to 0 and S equal to 1, the flip-flop, the output Q will be set, or it will become high. In the third situation, when I put R equal to 1 and S equal to 0, when I put R equal to 1, this gate will go in disable condition, implies that this output of this gate will remain 0, right? Then when it is 0, this 0 and this 0 will give you high. So Q bar will become 1. So when Q equal to 0, Q bar will become high. Up till now, it's okay. Fine, it is showing that Q and Q bar are following the rules, right? So Q is not equal to Q bar. In the last situation, when I try to put both are 1, so what happens? If I put both equal to 1, which implies that R equal to 1 and S equal to 1, implies that both the gates, gate 1 and gate 2 of NOR gate, are going to be in the disable condition, and both will become 0, 0, as I told you in this circuit. So both the NOR gates are going to be in the disable condition. And in this situation, what will happen? It is going to show you Q is equal to Q bar, right? So it is going to show you Q equal to Q bar, which is not allowed, right? So Q cannot be equal to Q bar. So we call it as this situation is equal to not allowed condition, right? So I'm writing here not allowed, NA, right? So this is a not allowed condition. When it sets, it will 0 and it is 1 and it is again not allowed condition. So we are having the first situation as the not allowed condition, right? So this is how a NOR gate can be used. The NOR gate can be used to make to implement a flip flop. Now, why it is called as a flip flop? Flip flop means at a certain position the flip flop flips, right? So it becomes 0, and sometimes it flops, that it becomes 1, right? So that is why it is called as flip flop. Now, flip flop is supposed to be a 1-bit memory storage device. This is actually a semiconductor memory device where we can store a 1 bit of memory, right? Yes. So I guess you have understood uh, how this circuit works. Now, just remember, we are going to replace this circuit. You should understand. I've shown you this two NOR gate circuit over here, and I'll be putting this in a block like this. So I will be using a block like this, which is having two inputs. We are calling it as R. This is S, and the output, two outputs are there, that is Q and Q bar. So we are going to call this as SRFF. So from next time, I'm going to use this block circuit, and you have to understand that in this block we are putting this circuit over there, right? So the circuit of NOR gate is there inside this block. So we are having these two terminals, R and S over here, and the outputs are Q and Q bar. But we are putting it in one box, and that we are going to call it as SR flip flop or RS flip flop, anything you can say. I guess you have understood the RS flip flop using NOR gate. Sorry. Now let us try the same circuit by using a NAND gate, right? So can we try this same circuit by using a NAND gate? Let us try on that. Uh, Yeah, now let us try the same circuit by using a NAND gate. So as I told you, so NAND gate can be used in this enable state, right? So when one of the inputs of this NAND gate are supposed to be 0, or if it is given ground, then the NAND gate lands in a enable condition, means the output of that NAND gate is going to be high. Now let us use the same circuit for implement the same circuit by using NAND gate. So I'm just replacing this NAND gate, NOR gate by a NAND gate like this, and this other conditions are nearly same. So I'm just dropping NAND gates over there. I guess it is proper like this. Okay. So just I have used a NAND gate instead of say NOR gate. Earlier we have used uh, NOR gates like this, and now I have replaced those NOR gates by NAND gates. So we are having a bubble over here in front. I guess it is not visible, but they are having bubbles. So they are NAND and NOR gates over there. The same circuit we are trying to use for the implementation of flip flop. Now, in this case, it's just a reverse of it. Now, let us see what happens when we apply this. It's the same condition like we have applied for, say, NOR gate use flip flop using NOR. Now this is a circuit again which we are calling it as RS flip flop using NAND gate. Okay, so let us try with this NAND gate. So yeah, again the same condition is there when we put 0 0 on both the conditions, so both the states. When we put R equal to 0 and S equal to 0, what happens? When we put R equal to 0 and S equal to 0, which means that we are having one of the inputs of both the NAND gate as low potential, then the gate is supposed to be in the enable state. Means the output of both the gates are going to be high. Now here it is just a reverse of that. In the last stage, or in the flip flop which we have designed by using NOR gate, the last state 1 1 we has given not allowed condition, but the flip flop using NAND gate. But in that circuit in which we are using NAND gate, when R equal to 0 and S equal to 0, both the output of both the gates are equal to 1, which shows again that Q and Q bar are equal, right? So both are equal, which is actually not allowed, right? So we'll call this as the not allowed state. So in the first condition, when we are using NAND gates, instead of uh, instead of NOR gates, the condition is not allowed, right? So when we apply R equal to 0 and S equal to 0, which will land both the NAND gates into enable condition, both the outputs will become high, and therefore we say that is not allowed. It will show you Q equal to Q bar, which is actually not allowed condition, right? So we say in the first condition that is not allowed. In the second situation, when R equal to 0 and 1 equal to S equal to 1, so R equal to 0 and 1 S equal to 1, right? So if one of the input of the gate is 0, it enables the gate, right? So S will give you Q equal to, yes, Q equal to high. So if one of the inputs to a NAND gate is equal to 0, the output becomes high. So the output of this first NAND gate is going to be high, which again says that when we put set equal to 1, the output is high, right? Another one, when we put R equal to 1 and S equal to 0, R equal to 1 and S equal to 0, which again shows that when S equal to 0, this will land in enable condition, that is 1. So if it is 1, this one and this one will give you, this one and this one will give you Q equal to 0, which shows that the flip flop is reset. So it is set and the other one is reset, right? In the last situation, when we apply both as 1 1, like 1 1, if you apply this 1 1, then it will land in no change condition, right? So when I apply 1, here I have to S and R. Now let us imagine that one of the gate, that is Q equal to 0 and Q bar equal to 1. So when it is 1, so 1 and this one will give you 0. Similarly, 0 and 1 will give you 1, right? So there is no change. So these two conditions are only going to change when we employ NAND gate to implement a flip flop, right? I guess you have understood the flip flops by using NAND and NOR. In the from the next classes, I'll be just using these sort of blocks where I'll be putting R, S, and the output Q and Q bar. The truth table is same like this, just for say just for NAND and NOR, the outputs are going to change over here. So here it will be showing not allowed condition, and here it will be showing no change. But the ideal truth table is like this only. As when we have 0 0, it should show you no change condition, and here it is going to show you not allowed condition. So we are going to use NOR gates only to implement the flip flop. And whenever I will say that I'm using this type of a block, you have to imagine that we are putting NOR gate implemented flip flop. So we are putting NOR gate inside it to implement this flip flop. And whenever we are when we are applying the inputs to R and S, it's going to show you this truth table. So this truth table is going to be continued to all the flip flops which we are going to study in the next class. I guess you have understood this flip flop. So that is why I have told you this NOR gate when it is in the disable condition. Whenever one of the inputs to a NOR gate is kept at high, the output of this NOR gate will become 0. Whether we will not care about the input given to the second. So if one of the inputs is high, then the output remains at 0. Similarly, for NAND gate, whenever one of the input is kept low or it is given ground, then without referring to the other input, the output will remain always high. And that is why we call them at enable state. And in the NOR gate, we call it as the disable condition. And this is how we are going to implement flip flop. I told you why it is called as a flip flop, because sometimes the output flips and sometimes it is flops, right? So that is why it is called as flip and flop. So it is going to change. This is what I have told you, that it is actually a 1 bit memory storage device. All the semiconductor memory storage devices is having these sorts of flip flops inbuilt inside them, and we can have an array of flip flops to store 1 bit of a data in one flip flop, and accordingly we'll have a huge data to store. We are having say pen drives on that. So pen drives are using this hard RAMs, in which we are have using RAMs in computers. Those are having semiconductor storage devices, right? So I guess we'll be studying more about flip flops in the coming classes. If you have any questions, you can ask me on that. I will love to answer you. I guess I have only 1 minute left for that. So do you have any questions, or shall we end the class? So yeah, thank you very much for listening this lecture, and I'll be again going to enhance, or going to taught you some more flip flops along with this. So be a part of this video series, and I'll be uploading this. Go through my YouTube channel, watch these videos, like, share, and say comment on this if you have any doubts. Thank you very much for this. See you soon in the next session. Thank you. Have a nice time. Stay home, stay safe, and take care.